Okay, thank you for the introduction. And before we get started, thank you for having me here. And also, congratulations on the 60th anniversary of the CIIE meeting. Okay. And it's really nice to see you guys all and the good friends. And also, it's always good to meet new engineers, students, scholars. So again, it's been the last time we met was 2019 in China, right? Okay. So we have gone through all those difficult time, and then now it's time to rebuild our relationship. Okay. So it's pretty much ready. All right. Okay. So for the next about 15 minutes, we're going to talk about the recent development of the recent development of the system, and also talk about the actual industrial cases. Okay, so let's get started. Okay, so let me move the. I can actually. Okay. Okay, so I prepared 4 different topics. So I would like to present the recent development of our research on the OHT system. So I'm going to give you a brief overview of what we have been doing so far and also introduce our recent advancement. And then I'm going to talk about the digital twin, how digital twin is developed, and also probably share the concept and also practical cases as well. And the third topic is the new paradigm on AMHS. So the overhead hoist transportation system in semiconductor manufacturing is the primary topic. But on the other hand, we believe that we are moving toward a new era in material handling systems. So we want to expand our focus, not only the OHT system, but also we want to talk about more interesting issues in practice. And also, you know that I'm always concerned with the new way of the education. So I'm going to talk about this as well. Okay. So you know that in background, the Korea is really a powerhouse of the high-tech manufacturing, like Taiwan. Right? So therefore, we both are really concerned with how to effectively operate the manufacturing facilities and including the material handling systems. So there are a lot of researchers now concerned with the effective operation. And the importance of material handling system getting a more increasing. So therefore, in the past, like 20 years ago, when I actually started my career, AMHS was not really main portion in the manufacturing operation, but now it's getting we got more attention from the industry. Okay. So I'm going to spend about a little bit of time where what is brief review what we actually did, and also after that I'm going to talk about the recent advancement as well. Okay. So I'm familiar with some students and also scholars who attended at the meeting in year 2018, year 2019. So I actually presented this one, but you can think this one is a little bit of overview. So you know that the OHT system, the material handling system in semiconductor fab. So you know that this is the actual fab in Samsung. Okay, so you know that the overhead waste transportation system, which system is the primary material handling system in the fab. But there are a lot of issues. So you know that most of the OHT systems, right? So there are 2 primary problems. One is the dispatching problem, and also dispatching means the allocating which vehicle it should be assigned a specific job. So it's a matching problem and also routing problems, right? But now we live in the era of the massive fleet operation. So we have to deal with thousands of OHTs. So one of the recent fab currently being built in Korea is that we have to operate more than 3,000 OHTs vehicles. Okay. But the problem is that that the congestion is a really big issue. Right? So it's really not easy to predict the congestion in advance, and also the unexpected events are always happening. So if that happens, then the engineers got involved in manually. So suppose that there is a congestion, then the engineers will keep watching the system and then they try to manually manipulate this one. That is the issue. And also, that the errors interrupting the flow happening all the time. So most common the interruption of the operation is the communication error. So if communication was disconnected, then vehicle makes a stop and then rebooting the communication system or rebooting the entire system. But it takes the 30 seconds to 2 minutes. You have to deal with a lot of vehicles and the vehicle stops in the middle of the track, then you expect a lot of the backlog. Okay? The backlog, not the backlog, the blockage. Okay. So therefore, if that is the case, then the engineers get involved into the operation and manually rerouting the vehicles. Okay. So that is a situation. But again, the problem is that we have to deal with larger vehicle and this manual operation. Okay, so is obviously limited. Okay, so therefore, we want to move parallel automation to autonomous. So automation is the industrial automation. It has two meanings. One is that it has to be repetitive, and also the predictable. So if there is no unpredictable event is happening, then there is no problem at all. You can just leave it as it is. But the thing is that the unexpected event is happening all the time, like communication error, and the vehicle makes the stops and also creates the larger conditions. This is happening all the time. And at the same time, the layout is get changed, and also the equipment is brought into the system, then you have to readjust pretty much everything. So you have to do it manually, everything. So therefore, the paradigm of autonomous means that the system understand the change the environment automatically, then adjust itself to meet the new requirements of the environment. So that is the paradigm of autonomous. Okay. So we are really inspired by the reinforcement learning. You know that the reinforcement learning has been around more than 30 years. So, but didn't get much attention except the control engineering community, right? But afterward the event AlphaGo that was held in year 2016 in Korea, then I was really surprised about the technology advancement, and then we decided to use this method. In the past, the approach was that using the conventional optimization, like integer programming or dynamic programming. So get the new information and run the optimization and try to find a routing, path planning, or the job allocation. But the problem is that you have to run this optimization all the time and also extract the data. If you deal with only limited number of vehicles, that approach should be okay. But unfortunately, you have to deal with thousands of vehicles, and conventional optimization approach has definitely limitation. Okay. So therefore, you know that there is a artificial intelligence, and these days, the machine learning is the mainstream of AI, and in the machine learning, supervised learning, unsupervised learning, and reinforcement learning, right? So the reinforcement learning is a part of the machine learning. Okay. So this is the result where, of course, I presented this in 2019. So you know that where if you use the conventional optimization technique, then you expect to have a larger condition. But if you use the reinforcement learning, then we prove that it's more effective. So that was the result. And also we applied this technique to the actual fab scale data. And this is the area where the wet bench diffusion and photolithographies are located. So we observed the chronicle congestion, but once you use our algorithm, then you don't see any problem at all. So you can see that. Okay. So, and also another interesting test is that we made certain area, we made a temporal pathway cutoff. So we let no vehicle allowed in this specific area for a certain amount of time. So we actually cut off the path, and then we actually observed what was going on, and then say that even though that is a totally unexpected event, but the vehicles are smart enough so that they could reroute by itself in a very effective way. So we actually compared the human operation and also AI operations compared together. But the engineers once got involved into it and tried to reduce the unexpected event, the congestion caused by unexpected event, but they couldn't handle the job effectively compared to the AI. So therefore, we proved that our approach is more advanced and also is a lot effective and also efficient in handling, even though there is a totally unexpected event occurs. Okay. And also, one of the benchmarking we compared was the approach developed in Georgia Tech, but we proved that the computation is a lot faster. Since we don't use the CPU, we use the memories and GPU, so therefore where the computation time is at least 10 times faster than the CPU. So that's why we guarantee the scalability, even though there is 1,000, 2,000, 3,000, but it doesn't, computation time is not increasing exponentially, so we can guarantee the computation. Okay. So pretty much everything was delivered. I mean in the paper over there, and I presented the more detailed issues and also modeling and algorithm in the year 2019 ISMI. Okay. So that was a quick review. Okay, and also those are the recent papers. Okay. The first paper is about the path planning, and the second paper is about the job allocation. Okay. Okay, now let's move on to the more recent development. So recently we tried the more advanced algorithm, the GNN, graphical neural network, and also we move on to the area abnormality detection. Okay, and also the commercialization of the system. Okay, so let me talk about this. Okay, so the current method, the method I presented, it's in general it is okay, but we found some caveats. Okay, caveat means that something we anticipated before, but it's more like a bug. It's not. We can say it's a bug. Okay, the problem is the following. Okay, you know that the Q running algorithm is that it's you learn by try doing something, right? So therefore, suppose that there is a vehicle and vehicle is traveling from node 2 and node 3, then once it completes the node traveling, then this vehicle sends out the signal. Oh, when I just completed the traveling from node 2 to node 3, and it took, for instance, 20 seconds. So it sends out the information, and then this information is shared with other vehicles, right? And the other vehicles actually get this information, and then they actually use this information for their traveling, making paths, okay? But let's think about the following case, okay? Suppose that there is a one vehicle got stopped, and it's just covering the node point 3, right? Then what's going to happen, right? So this vehicle is broken, and also communication error is happening, and also the vehicle following, right? It doesn't actually receive any information from this vehicle yet. That is because the vehicle couldn't send out the signal because of the error, right? Then the vehicle following just entered to the node 2 and 3, the arc, and then it's going to create the severe blockage. But the information is not sent. That is because information can be sent only when you complete the travel from node 2 and node 3. But the rest of them hasn't actually completed the travel yet. So therefore, it's not sending the signal, the following situation. So therefore, the vehicles are coming in, and then it's make the situation a lot worse. So therefore, already now, suppose that this vehicle right in front is got fixed, okay? But the problem is that after this one is fixed, the rest of the vehicle will make a travel, and then it's gonna send out the signal. Oh, normally it takes 20 seconds, but now this time when I traveled from node 2 to node 3, it took 50 seconds, 55 seconds, 60 seconds, 70 seconds, and it's gonna make all those Q values increasing. Right? If that happens, then even though problems got completely resolved, since Q value is really high, then the rest of the vehicle will not select this node. That is a trouble. Okay, that is a problem. So therefore, of course, it use the exploitation and the function. So even though Q value is really high, but the randomly it's going to actually explore the new area. So it's going to be eventually fixed, but it's going to take time. Right? So therefore, this video clip actually explained what I just described. So for instance, in this video, this is there is one of the vehicle actually has trouble, and it is creates the all those congestions. So let's take a look at this one, okay? So now there is a trouble, all those vehicles got stuck now, okay? But okay, so troubled vehicle got fixed. Now it's going back to the normal condition. So everything, all those conditions got cleared. But the problem is that since the Q value within this area got increased, then no vehicle actually try to enter to this area. That is the trouble, okay? So even though we cleared the congestions, but since the Q value had been increased, no vehicle tried to enter this area. Okay, that was the trouble, right? So therefore, what we are trying to do is that we try to actively anticipate. So we update the Q value after vehicle makes the travel, right? But now we try to actively anticipate the situation. Okay, so that is called a active update. So we use the various techniques in the past, and also we try to see the two cases. One is that is it good to have a predictable model so that it's going to actually eliminate this kind of trouble? That is the first question we had, and the second question is that what about the predictability? Is it really we can predict the future? So those are the two questions we try to answer. So we made certain models and also try to predict. So based on the number of vehicles got stuck and the number of vehicles in between the nodes and also other factors, and we try to predict the Q value. That's what we did. And then we made a certain level of a progress. So if you use the post update, let's take this one, okay? So you know that the vehicle got stuck in here, but now active update predicts that, oh, there is a trouble. Okay, so now vehicles got rerouted automatically. So you can see that in the active updates, right? Okay, and then now, so the vehicles keep entering in the previous one, okay? And then now the trouble got cleared. But this figure, take a look at this one. The left-hand side even though it's a lot efficient to move straight line, but it doesn't actually enter to the area. But in the active update, it takes the shorter route effectively. Okay, so we proved that. So this study we actually completed about 2 years ago, and then we saw that the approach of the active update is promising. Okay, promising. But the trouble is that this is the hypothetical production line. Okay, so the goal of this study is that direction of this research, is that valid or is that doable? So we wanted to test it, and then we found that it's promising. Okay, so by the way, this is a result. Okay, for this one. So the graphs represents the active update. On the other end, the blue one is the post update. You can say that the average delivery times got improved, okay, with the active update. And also at the same time, we could cut out all those long tail here. So there are some cases that requires a lot of the delivery time, but we could actually get rid of that. So that is our achievement, okay. And then now what we are trying to do is that the model itself, we have a limitation. The active update we did was that we used the conventional regressive model, but you know that the model gets bigger and bigger, then it's really hard to predict. Okay, so in a limited environment and so limited number of vehicles, then it's doable. However, it doesn't have we can guarantee the scalability. That's why we decided to use the graph neural network. The graph neural network is that in the Euclidean distance, we try to predict pretty much everything, incorporate all those features, then that actually puts a larger burdens into computation. But the graphical neural networks, we actually extract a certain data based on the network model. So therefore, the amount of information we there is significantly reduced, and only we care about the relationship between the node and arc. Okay. So we believe that this graph neural network model really fit into our needs. Okay. So one of my students, Mr. Lee, he's going to actually present more detail of this study, his ongoing research. So this is not complete. It's not completed yet. It's still ongoing research, but at least we show that it's promising. Okay, so he's going to actually deliver a talk. Okay, and also this is some limited. It's still limited the outcomes. Okay, but still, it's promising. So therefore, even though we can actually use this graph model for the entire the network, but it shows a pretty good predictability for very short term, like weather forecasting. We can forecast the weather for the next couple of days, right? But if we are to predict the weather for the next week or week after or a month after, then it's not well predictable, right? So, but at least, well, if you are to predict a very short-term future, then we prove that it's doable. Okay. Okay, so that is the one of our recent progress. Okay, and the next one is the abnormality detection. So you know the abnormality detection. There is the vehicle is moving around, and also sometimes it makes a certain problems, certain errors. But predicting this error is really challenging. But at least we want to find out if there is error. Then at least we want to find out this is the condition is some serious condition or something like that, right? So therefore, we use the autoencoder and also the variation of the autoencoder the approach, okay, and then we try to predict the abnormality. So you know that the autoencoder based approach is that we try to understand the normal, right, and then predicts the abnormal, right. That is because the space of the abnormal is pretty much infinite, right? But at least we know projects the space of the normal conditions, right? So therefore, one of the feature extraction approach, the abnormality detection, and also using the deep order encoder, deep order encoder. Then the predicting the abnormalities such as the current or the mechanical errors or the instability of the systems. So it's also promising. So this research will be also, we're going to talk about the more details about this research tomorrow. And at the same time, we're going to add this abnormality detection to the entire operation of the vehicle, which means that, that it's a vehicle is a mechanical system, electromechanical systems. And we have to deal with thousands of vehicles. And we observe that each vehicle has its own properties and also its own characteristics. Okay? So suppose that there is a vehicle making trouble all the times. It's a little bit unstable. Then we don't want to give this vehicle job for long distance, traveling in a very critical condition, the area. So therefore, we actually segmentize the group of the vehicles. Also, this group of vehicles, they never had any trouble, and they are really excellent. Okay, but some vehicles, it's really unstable. Then we give this job to the job for a short distance travel, or the job can be done in a less congested area where we can actually perform the maintenance more easily. On the other hand, those vehicles perform the job really well and is very stable, never had any errors or trouble. Then we actually give the job for long distance and then going through the very congested areas. Okay, so we proved that by segmentizing the state of the vehicle, and then it could effectively operate the systems, and also we can actually have a more robust system. We proved that. So this research was the outcome came out 6 months ago, and I'm currently in the process of actually putting all those findings for a journal publication now. And then so that was the first topic, okay? And then let me quickly go through the rest of the topics for the next 50 minutes. So let's move on the digital twin, okay? So I believe that you heard, right, digital twin. So we want to create a digital area. So the virtual system that actually imitates the behavior of the actual system, and this system is acting like a twin. So that's why we call it digital twin, okay? But the term itself, digital twin, has been around and also used for many different cases and many different situations. So the definition itself, it becomes a little bit vague, right? So in this one, digital twin, my definition, okay? So I follows the definition stated by those two guys from NASA and Air Force. Okay, so I read some papers, and I believe that this is the concept that really matched to the direction where I want to move to, right? So therefore, in this one, okay, so those guys are from NASA and Air Force. So if you read that the goal of the digital twin was the certification, fleet management, and sustainment. Which means that certification means that you develop a product, and also you want to verify and validate the products. That is first one. And the second one is the fleet management. We want to actually perform the effective and efficient operation of the system. And the last one is the sustainment, means that it's maintenance. Okay, so three areas: product development and operation, and also maintenance. They really focusing on to, right? So this really fit into our needs. Okay. And the next one is that it has to be a real time. So therefore, in order to actually do something, then it has to be a real time communication. That is one requirement. And then another requirement is that it has to be integrated one another, right? So we have to deal with complex system, and also we have to guarantee a certain level of fidelity. Then it has to be a military display, and integrated system one another, right? So their concept was that they actually in the paper they didn't actually define, however, implicitly stated that DT is integrated multi-physics, multi-scale probabilistic simulation, and to use to mirror the life of its corresponding flying twins. By the way, they are NASA engineers, though they are more concerned with aircraft and also the space systems, right? And with high fidelity physical models and also extensive data analysis. But my interpretation of their meaning is that I define the concept of DB as follows. So goal is that effective product design, operation, and maintenance. Okay. Key requirements are as follows: communication between the real and virtual systems, and also multi-hierarchical integrated system for high level of fidelity, and also support the decision making or the functional requirements. Okay, those are the with the extensive data analysis. So that's my requirement. So now I'm actually writing a paper targeting to the next year's case conference. But we're going to actually show more details of why we need those requirements. There are good examples, okay, meeting these requirements in our daily life, okay. First one is that, so daily life example, the GPS, and also the real-time traffic-based the navigation system like Google Maps or the other maps, right? So in this one, so one of the requirements is the communication. So GPS signal and also real-time traffic signals are synced together, and that is shown in the virtual environment, the virtual map. While you are moving, the GPS signal actually follows you, and also it shows in the virtual system. So that meets the first requirement. And also, the second system is that there is a GPS signal, there is a map, and also there is a traffic signals or traffic conditions are actually integrated. So it's a multi-level. The map information, my position, and also traffic information, and also the shortest routing algorithms are multi-layer problems, right? So they are actually integrated together. And the third one is that what is that? It should support functional requirements or decision making. So I want to make a decision out of this, right? So therefore, that meets the three requirements. So therefore, we can actually estimate my future, or if I follow those paths, then I will be arriving at the certain area in certain amount of time, or in the future, right? So we can interpret that this one as an extension of our time. Another example is the screen golf. So indoor golf is very popular in Korea. So you know that if we are play golf, but I don't have enough time to travel and it's way too expensive. But in the limited space, I play golf like as if I were in the actual field, right? So therefore, there is a sensor. When you hit the ball with your club, then the trajectory of the ball is immediately evaluated. So it's almost a real-time evaluation of the system. And then the projection of the ball is shown in the virtual field, right? And also it shows all those. So the ground is tilted, and also based on all those informations, right? So that it imitates the environment. Okay. So in that sense, that I want to play golf, and as if I were actually playing the golf. So that is functional requirements that actually provides these functional requirements, right? So therefore, if we play golf in a limited space, but we can feel that we are actually playing golf. So therefore, it's an expansion of our space. So the interpretation of the digital twin actually can be the expansion of our time and expansion of our space. Okay, so let's move on. So what we created was that in the OHD system, the PLC connection, then we created all those data, and we actually made the system so that the digital twin environment represents the actual, the physical, the factory, and also we collect the data and send out the data, and also it actually integrates with the MES system, MCS system, and also other controller in the equipment. Okay. So therefore, we actually imitate the actual system as if those systems are running in the actual factory. And also, the reason we really need this system for the AMHS is that the OH vehicles, we have to deal with 1,000 vehicles at least. But we cannot test those vehicles unless they are actually installed. But if we don't discover the problems before we actually physically install, then we were in trouble. So therefore, in the virtual environment, we need to perform the extensive analysis. Okay? So this is the virtual factory. So you know that we made the system. The graphic is the designed with Unreal, but it's not just the animation. Actually, the physical connection, the PH controller and the system, and the send out the signal and communication with the NGS, all those are done, and that is graphically represented in here. So that is the actual system. Okay? And then our AI algorithm is running underneath. So therefore, it's a multi-layer system. So there is a PLC hardware level, and also an AI algorithm level, and MCS level, and also virtual factory level. Factory scenarios running all together, and then put them all together, and then we need to make sure that our algorithm is okay and our hardware is okay. So we are testing to do that. And then, you know, also our customers are trying to use this for the traffic management as well. So we want to run the several different scenarios, and we need to make sure that everything is okay. So, for instance, like this one, okay, so suppose that there is a new machine is coming in, and also traffic pattern might be changed. And if that is the situation, then we might be in trouble, something like this one. So therefore, we need to come up with the better scenarios, and it actually searches through the better scenarios automatically, and then we actually are prepared for this unexpected event. Okay. So we prove that. And also, one of the benefits of this one is that obviously we can improve the key performance, like the average delivery time, and also the throughput. The number of lots we can actually process within certain amount of time. And also, using this one, we actually show that we could reduce the 20% of capital investment. So each one vehicle costs more than $60,000. It costs the Mercedes-Benz each vehicle, right? But if we deploy the 1,000 vehicles, but we can cut down the 20% of our investment, then that's a huge cost saving. And also, this one is we used for the risk management. The recently South Korea companies, we aggressively moved to the electric battery manufacturing. So there are manufacturers are building aggressively pretty much everywhere. It's the United States and also Eastern Europe and also some the Southern Asia area. So a larger factory needs to be built, right? But the problem is that the electric battery, it's a new industry, so nobody actually had a experience. Then there is an equipment supplier, AMH as a supplier, AGV supplier, then IT system supplier, MES and system. Where there is a certain target production date. We have to meet this one. We need to make sure that everything is running okay. But once everything got installed and also try to integrate them together, but suppose that there is a protocol errors or the controller errors, then we have to delay our target dates. So therefore, now these days, the companies want us to actively test in a virtual condition before they actually brought into the system, into the actual physical factory. Okay, so that's why we need a digital tool. The actual application case is following. Well, we worked with SK Innovation, the SK Citroen. That's the number 3 wafer manufacturer in the world. And then using this OH algorithm and also the digital twin, so we could deploy the system within 4 weeks. Okay, usually it takes a month, 3 or 4 months at least. But we actually use this one, and also the actual job was done in 4 weeks, and also we spent an additional 2 weeks to make sure that everything was okay. So again, it's not something, technology is not something just to remain in the paper, but also technology has been proven to the actual industry. Okay. Let me actually quickly go through this one. So this is the new paradigm in AMHS. That's what I see. You know that industrial automation, this is the image you can think of. So it's a conveyor belt, and also workers are just doing the same job repetitively. But this paradigm has been around more than 100 years, right? But now it's changing it. The problem of the conveyor belt is that it's not flexible enough, right? So therefore, these days, we are moving the paradigm. It's a conveyorless, beltless line. Okay, so there is no conveyor belt, and the vehicles are carrying the work in progress inventory and visually, right? So one of the factories we work industry, the car manufacturing, where the if you see the layout, conventional layout is that there is a long conveyor belt using U shape or S shapes. But now, for these days, the car manufacturer, if you look at the layout, then it's like the open chessboard. Okay, it's scary. So you can see that. Can you see the size of the person over there? You can see the image in the size. Right? So therefore, the robot-based, massive clip-based, the material handling system is the really future. And also the semiconductor battery for electric vehicle and also flat panel display, they are also trying to adopt a three-dimensional moves. So there is OHT and also Stocker system and AGB and AMRs integrated all together. The problem they have right now is that OHT vendors and Stocker vendors and also AGB vendors, AMR vendors. AMR means the autonomous mobile robot. They are all different vendors. They have different protocols, and there is not synchronized altogether. There is a lot of efficiency. So my job is to integrate them all together and to provide a solution for that. So this actually gives a new the area in industry. So in the conventionally, there is an MES system, MSS system, and the individual controllers, mostly conveyor controllers. So now we have robot collaborative intelligence solution. This is a new segment. It's coming in. Okay. So therefore, and also this one is the conventional material handling system engineers. They only I don't know whether you are familiar with this one, but the starting point is the front to table, right? But you don't know that this front to table, it doesn't actually incorporate a lot of information. So therefore, the material handling system design, education has to be changed. It starts with the capacity planning, layout design, manufacturing IT system, and also algorithm development. So everything has to be from the holistic view. By the way, another recent paper I'm currently working on is that the number of vehicles and number of buffers and also the material flow, they are closely related to each other. So we found very interesting result. Okay, so probably sometime next year we can present more detailed, more theoretical aspects of the system design. Okay. And also even car manufacturing, you know that the HV is carrying the whip. Also, this AMR is supplying all those parts all together. Okay, you saw that importance. This is what I described. The process robot and also HV robots, material handling robots, they are not safe together. So sometimes the process robots are making idle because proper parts are not delivered or something like that. So that's the things we need to solve. And also the parts feeding mechanism is also automated. So in the factory, in the basement floor, there is a huge the inventory, the part inventory system. So in here, we also develop a system. Okay, so in here, okay, according to the deadline is also a critical issue, but we successfully completed more than 20,000 deliveries. So this work will be presented at this December Winter Simulation Conference by one of my students. And also this is the digital twin we created. So this is the factory environment. And the left-hand side is the user interface, okay? And the right-hand side is the digital twin imitating the factory floor, okay? Oh, by the way, this is the DIME research, DAIM. D stands for digitalization and AI. So AI is AI, artificial intelligence, and M is manufacturing. Okay, so DIME Research is a company founded by the four PhDs, including and also myself. So we started this company year 2020, And then, these days in Korea, where the Korean government actively promoting the social and industrial value of the engineering, the outcomes. Okay, so there are a lot of supporting programs run by the government, and the government really pushing the scholars do something for the industry. So that's why we actually found the company, and one of my PhD graduates and also one of the co-founders, he's already there. And so we delivered the system. We now have 26 team members in the company, and we recently got investment from one of the major venture capital. Is the total investment funding was a little bit more than 10 million US dollars. Okay, and then the last part is that education. You know that I told you that the massive fleet-based material handling system is now trend in industry. Then, as a professor and also scholars, we need to actually educate and training the engineers and also students, right? So therefore, for 2 years ago, we set up the a research lab. So we actually set up those are the actual systems used in the lab. Okay, so we created a laboratory environment. Okay, so we checked a lot of data, and also there are a lot of opportunities. Originally, where we tried to actually open up all those data for this community, so that you can actually develop the more advanced research, realistic research with the actual data. So probably it's got delayed, but we will release all those data by sometime next January. So if you are interested, please let me know. Okay. Overall, you can actually participate this data, the open data platform development. And also, this is AGV test bed, so we have a test bench available. And also the conventional Lego stuff. Okay. And at the same time, so this is the Lego AGV. Okay, so you play with the Legos. So you know that Lego guy. Every time I came here, I present. So we have tested that, created. That was too bad for the last 2 years, where we couldn't do much, right? All those the class ran online, so therefore the students didn't have much the experience playing with all those the Lego system. So therefore but now it's we running the class in person. So and also actually we brought this system. So maybe I can actually give you the demo. And also there is I will talk about more detail about the education tomorrow afternoon. So probably before the session or after lunch, maybe I can actually show the demo of the system. So this is the AMR. Now conventional AGV got replaced by the AMR system. And also we are also concerned with dealing with those AMRs. We have 100 AMRs altogether. So this is a Raspberry Pi based, but all the physical part is assembled and put together with the Lego pieces. So it will be pretty interesting. Interesting. Okay, so that is it. And again, well, thank you for having me. And also if you want to hear more about detail, that there is some afternoons tomorrow. There are multiple sessions. Okay, thank you.